Right, folks, here we are on the, section 3.5. This is at the top of page 10 of your chapter 3 notes. We're talking about the polygon angle sum theorems. But first, we're going to talk about what is a polygon, what is not a polygon. So we have three little rules here. A polygon is a closed plane figure. Closed plane figure. Right, a plane figure meaning it's going to be two-dimensional. It's not going to be anything like a cube or a box or a cylinder or anything like that. Enclosed meaning it can't have any open sides. It has to be completely closed. The second part, it's got to have at least three sides. And that makes sense, in fact, with the first one, is if you have something with just two sides, you're never going to be able to close it off without a third side. So that's why we have that rule. And the last one is sides can only intersect at endpoints. Right, so what that means is you can't have any crisscrossing lines. The only time the two sides are going to meet are at corners or vertices. Right, so we have three examples here. The first one, this is closed, and it has at least three sides, and none of the sides are crisscrossing in any way, so this is a polygon. The second one has at least three sides, and there's no crisscrossing lines involved, but it is an open figure because it is not closed off here, so this is not a polygon. It is not closed. And the last one is at least three sides, and it's closed, but the problem is you have these crisscrossing lines. These two sides intersect right here, and that is not an endpoint, because you have from A all the way to C, from D all the way to B, so this is not an endpoint whatsoever. So this violates the third rule up there, so this is not a polygon. And our explanation is intersection is not an endpoint. Alright, to name a polygon, you have to follow two simple ideas. You're going to start at any vertex. So you don't have to start at A just because it's the first letter in the alphabet or anything like that. You start at any vertex, and you want to list all the vertices in order. List all vertices in order. And that can be clockwise or counterclockwise. So when it says in order, that means you need to start one spot and go all the way around here or all the way around there. You cannot crisscross. So up here you could not call this A, D, B, E, C. That would be wrong because you're crisscrossing, right? So you pick any letter as a starting point, go all the way around one way or all the way around the other way. So example 1 says list these two names for this polygon. There's a bunch that are possible here. Let's say you wanted to start at the letter P. You can say PACM. Let's call it a polygon. Polygon PACM. And for the second one, let's say for the second one you want to start it at M, and you wanted to go the other way around, so call it MCAP. And there are actually 8 different possible answers here, because you could start at any one of the corners, and you could go counterclockwise or clockwise, so it'd give you 8 possible answers, as long as you did them in order and you listed all the vertices. So you could never call this polygon PAC, because that makes it sound like a triangle, because there's only 3 vertices listed. Since this has 4 corners, you need to have all 4 letters in the name. Alright, onto a new idea here. Talk about the difference between a concave and convex polygon. Right here we have one example of each, and to figure out which one is which, the easiest thing to do is you're going to connect all the vertices that aren't already connected. So like right here, here's a vertex. It's already connected to this one and this one, but it has not been connected there or there. This corner here is connected to the left and to the right, but it needs to be connected to this one, and over here to that one. And let's see, this also needs to be connected over here. And yeah, that takes care of all of them. So if you do that, and all of those diagonal lines you just drew, or those dashed lines you just drew, if they're all inside the polygon, that makes the polygon convex. Over here, if you try to do the same thing, you can start to see there's some on the inside, so it looks like it's going to be okay, but if you connect this vertex with that vertex, all of a sudden it's on the outside, so that cannot be called convex. It must be a concave polygon. How do you remember between those two? Because they sound a little familiar. They both start with CON. Well, here's one way to do it. To be concave, it's almost like this object has to cave in and come back out. That'll create an outside diagonal, and that's what makes it concave. So on the bottom here, it'll say all diagonals are inside the polygon, and over here, all the diagonals are not inside the polygon. And that's how you figure out between concave and convex. Right, flipping the page here, we're going to talk about different polygons and their names. Right, most of these you have heard before. We're looking for the most general or most generic form of each one of these. Like for instance, for number 4, we're not going to put the word square because that's too specific. We're kind of coming up with the most broad or the most general term to describe each one of these. Well, the first one's nice and easy. A three-sided object is a triangle. Something with 4 sides. We know lots of them, right? You have trapezoids, you have squares, rectangles, rhombuses, all those sorts of things, parallelograms. But the most general term is a quadrilateral. So that's what we're going to put there. A quadrilateral. Right, then an object with polygon with 5 sides is a pentagon. With PET usually meaning 5, like a pentagram has 5 corners, pentagon has 5 sides. Quadrilateral, you see the quad there usually means 4, like a quad's got 4 wheels. And you're familiar with the tri always meaning 3 things. So a 6-sided object is a hexagon. Eight is an octagon. Same way an octopus has 8 legs. 9 sides. This one's a little trickier compared to the other one. This is a nonagon. 10 is a decagon. And you think of a decimal. Decimal places are based on the powers of 10. And a decade is 10 years, things like that. So there's DEC standing for 10. 12 is an unusual one you may not have heard before. It's just like this word right here, decagon, but it has D-O in front of it. So it is a dodecagon. Dodecagon. And finally, if there's n sides, like you don't know exactly how many sides there are, then they just simply call that an n-gon. Like if it was 22 sides, it'd be 22-gon or whatever. Right, the one that's, these are the words you're going to be responsible for. You can tell right here there's missing 7 sides because it's not used all that often. 7 sides, you might remember, is a heptagon, H-E-P-T, a heptagon. But we're using the table that's in the book, so those are that's what's in the book, so those are the ones you're going to be responsible for. Right, Theorem 314, the polygon angle sum theorem. It says the sum of the measure of angles with n sides is going to be this little formula here. You're going to take n minus 2 and multiply by 180. So if you're asked how many how many degrees, if you added up all the interior angles of something with 21 sides, you'd put 21 here. Right here they're asking for a hexagon, so that's what we're going to use there. Example 2 says find the sum of the measures of a hexagon. Well, a hexagon has 6 sides, we mentioned a minute ago, so we're going to put in 6 there. We're going to start with our little expression. We're going to put in 6 for n, because that's how many sides a hexagon has. And now you want to calculate. You're going to do what's in parentheses first, following the order of operations. It gives you 4 times 180, and that is equal to 720. So if you draw any hexagon whatsoever, measure all 6 angles on the inside, add them up, it's going to be 720 degrees, always, no matter what. Big ones, little ones, ones that are perfectly drawn, ones that are lopsided, anything at all. Any hexagon whatsoever is going to add up to 720. Right, here's a practice problem. You're going to do the exact same thing, but with a decagon. So you're going to start with the same expression, but you're going to plug in a different number here because you're dealing with a different object. So go ahead and pause the video, figure out how many degrees are in the total for the angles of a decagon, and we'll go over the answers in a few minutes. Alright, to go over answer for the practice problem here, you're going to start with the same expression for the sum of the measures of the interior angles of a decagon. The decagon's got 10 sides, so that's what we're going to put in for n. We're going to subtract first and get 8. And now you need to multiply 8 times 180, and that gives you 1,440. So there's our answer. So you draw any kind of decagon whatsoever, measure all 10 angles, and add them up, you're going to get 1,440 degrees every time. Alright, we're going to take care of example 3 here before we stop the video. It wants to figure out how big angle B is in this quadrilateral ABCD. So it gives you this 100-degree angle here for A. D is a right angle because it's got the box, and it does tell you that B and C are equal to each other. So there's too many unknown things here. What you need to figure out is the total, what all those are going to add up to. Now some people know off the top of their head that a quadrilateral is going to add up to 360 when you think of rectangles and squares and things like that, but that's actually true for all quadrilaterals. Let's just pretend for 1 minute that you don't remember that quadrilaterals add up to 360, so you need to figure out the total. So use our little expression we just learned there. Plug in 4 because a quadrilateral has 4 sides. Subtract first, and then multiply, and sure enough you get 360. So that's what our total is. So we're going to take 360 degrees, and we're going to subtract out 100 because we know the angle A is 100. That leaves us 260. We're going to subtract out angle D, which we know is 90 because it's got the box there. That leaves us with 170 degrees. All right, so there has to be 170 degrees remaining in those 2 angles. Now, normally you'd be stuck there, you wouldn't know what to do, but since they are equal, we want to take that and divide by 2 and split it up equally. And that gives you 85 degrees for the measure of angle B, and it would also be the measure of angle C. And you could have also used algebra here if you're an algebra person, because you could have set up x for your unknown, another x because you know it's going to be equal to itself, so you have another x there, plus the 100, plus the 90 equals 360. You combine like terms and solve, you'd get your same 85 degrees as your answer. All right, we're going to pause that there and pick up the remaining part of section 3.5 in the part 2 video. We will talk to you next time.